Medium to heavy-duty diesel trucks emit large amounts of dangerous emissions. In order to combat this, increasingly stringent emission standards are requiring automotive manufacturers to find new, innovative solutions to this problem. One of the main ways emissions are reduced is an exhaust aftertreatment system. A typical exhaust aftertreatment system contains a diesel oxidation catalyst, a diesel particulate filter, and a selective catalyst reductor. These catalysts operate in concert to convert dangerous pollutants such as hydrocarbons and NOx into more environmentally friendly gases. However, a potential problem with this strategy is that at low temperatures, emissions cannot effectively be treated. In order to counteract this, Tenneco is instituting a fuel burner upstream of the system, with the goal of increasing exhaust temperatures to optimize catalyst conversion efficiencies. Our role within this fuel burner implementation was the creation of a control scheme, which would reduce NOx output by 50%.
To simulate and test this fuel burner, our customer provided us with a complete exhaust aftertreatment system in GT Suite, complete with a CTSU or fuel burner upstream of the DOC and other catalysts. Our fuel burner controller was made in MATLAB Simulink in order to co-simulate with this GT Suite model. Our customer requested 2 different control schemes, and after engineering design comparisons, we chose to build a simple temperature controller and a more complex enthalpy controller. The temperature control model uses a PID with temperature feedback from the inlet to the exhaust. To predict the burner needs and induce a needed temperature change, we use thermodynamic equations relating a delta T to a needed fuel rate to the burner. Because cold start is one of the highest peaks in emissions and NOx, we implemented an open loop control to make sure the SCR gets to temp as quickly as possible at the start of a cycle. To make sure the burner doesn't overheat in the system throughout the cycle, catalyst temperature limits are used to shut the burner off, and even using air to cool the system around dangerous catalyst temperatures. Running this simulation, our primary goal is to increase SCR temperature to above 210 degrees Celsius to optimize NOx conversion without exceeding catalyst temperature limits or wasting fuel. The final PID tuning was done comparing overall NOx conversion efficiency and added fuel consumption of the burner.
In addition to the features encompassed in the temperature controller, the enthalpy controller utilizes distinct functions in hope of adding robustness to the control strategy. This controller calculates approximate enthalpies required to heat each of the exhaust aftertreatment system components, the enthalpy added by the exhaust gases, and the required enthalpy to be added by the burner in order to maintain an SCR inlet temperature of 210 degrees Celsius. It then transfers this required enthalpy to mass flow rates of air and fuel supplied to the burner. This method was used to more accurately represent and predict the response of the system.
2 separate test cycles were run for both controllers, the Federal Test Procedure, or FTP, and the Cruise Creep, or CC, cycle. The SCR temperature stayed above 210 degrees Celsius for the majority of the duration of both tests. Cumulative NOx emissions over the FTP cycle were reduced by 49.6% with the enthalpy controller and 64.5% with the temperature controller. For the FTP cycle, the enthalpy controller missed the NOx emissions constraint by 0.4%. There was also some overshoot in the catalyst temperatures for both controllers during the Cruise Creep cycle. The next step for this project is to take these concepted controllers to hardware for testing within a dyno. Eventually, they may become commonly used in exhaust aftertreatment systems.